It's being recorded.
Yeah, it has agreed now. I think the ones who are refusing have been kicked out, but they will join again. So I'll share my screen. Can you see the screen?
Yes, sir.
Yes.
So today we'll be dealing with what? Last time we were around here. So we did all this. We stop here, right? And this is where we stopped. Is that correct?
Yes.
How?
Yes. Yes. Yes.
We shall
Yeah.
just review the theorem that we proved. So this is the last thing we did, the order of an element. It was in this topic, order of an element. So it says the following: let G be a group and let A be an element in the group. So if we know the order of A, we can find the order of any other power of A. So if M is any other integer, it's possible to find the order of A raised to M, where A raised to M is some power of A. And we can obtain that as N divided by the GCD of M and N. So anytime we know the order of A, we can fix any other integer, say M, and we'll be able to find the order of A raised to M. So now you will see clearly that the two orders will be equal. The order of A and the order of A raised to M will be equal if the GCD of M and N is equal to what? The only way these two sides will be equal is if what happens?
When GCD of M and N is 1.
Yes, that's correct. So I keep that in mind. So we already proved this, so I will not go through the proof. We were just reviewing the theorem because we may need it in some of what we shall be doing. So that's the proof itself. But there are some consequences of this theorem. The first one is this. If the order of A is equal to N, then the cyclic subgroup generated by A will be equal to the cyclic subgroup generated by A raised to M if and only if M and N are co-prime. Co-prime simply means M and N have greatest common divisor equal to 1. So another word for co-prime is relatively prime. So let's see if we can prove this. I've only proved it in one direction. We have assumed that M and N are co-prime, and therefore the GCD will be equal to 1. And therefore we can find the order of A raised to M to be N over GCD Mn. But we know that GCD of Mn is 1, so this will just be equal to N. And therefore the order of A raised to M will be equal to the order of A. Since they have the same order, it means the cyclic subgroup generated by A will be equal to the cyclic subgroup generated by A raised to M. Because the two elements are of the same order, and any element in here will be So I think that's clear. That should be clear from we talked about cyclic subgroups earlier. That we know that the order of an element is equal to m, then the cyclic subgroup generated by that element will also have m elements. Okay. So that's what we are using to make this conclusion. Order of A is equal to order of am. Then if you get all possible powers of A and all possible powers of A raised to m, you'll end up with the same set. So that these two cyclic subgroups will be equal. So another result here, it says that a cyclic group of order n has phi n generators, where phi is a Euler function. I don't know if you're familiar with the Euler's function. Euler's function is basically, it counts the number of positive integers which are co-prime to n but less than n. So for instance, if I have phi of 4, I'll need to count the number of integers which are less than 4 and co-prime to 4. How many are those? Anybody? If n is equal to 4, what is the value of this function at 4?
2.
2, because we have only 1 and 3 as the integers which are co-prime to n. So we just count those, there are only 2 of them. What about if n is equal to 7? What is the value of this function at 7?
3.
You counted 3. Anybody else? I think 3 is not correct. 7 is a prime number. So if any number smaller than 7, any positive number smaller than 7 will be co-prime to 7.
They are 4.
They are 5.
6.
Hey, this number is
5.
changing too much.
5.
It's a very volatile number. There are 6. All the numbers, 1, 2, 3, 4, 5, and 6, all those will be co-prime to 7. And there are 6 of them. So this function will have the value 6 when n is 7. So let's do it one more time to see if you have understood. What about when n is equal to 10? What about when n is equal to 10?
4.
4. 4.
So 4 is a number. Which numbers have you picked?
3, 7, 9.
Pardon?
1, 3, 7,
9.
1, 3, 7, and 9. Okay, that makes sense. So basically what this corollary says is that if a group is a cyclic group of order n, then the number of generators it has is phi n. So to prove this, we have been told that G is a cyclic group, so it must be generated by some element. So G, suppose the generator is A, so G will be equal to the cyclic, will be generated by A, and this will only be equal to A raised to M. Any element in G will be some power of A, right? So any other element of G will also be a generator if the order of that element is equal to the order of A, correct? But this only happens if the GCD of M and N is equal to 1. This is because we know that the order of A is equal to N. This is from the previous theorem. So the number of possible values for M will just be phi n, because M will simply count the number of integers which are smaller than n and relatively prime to n. So for instance, if the order of A is, suppose the order of the group is 10, So if this is 10, that group will have how many generators? Exactly 4 generators. As long as it's a cyclic group. Remember here we are very specific, not all groups. It's very specific. We are talking about a cyclic group. So you can always count the number of generators or know them beforehand. So I think we have looked at some examples before. Let's look at this now. How to generate the cyclic subgroups and find generators. So I think to illustrate the first corollary we have looked at today, if you consider the dihedral group of degree 3, we know that the order of this element A is equal to 3, right? We also know that we now want to find the order of A squared. If you use our formula, the order of A raised to 2 will be equal to 3. That is the order of A divided by the GCD of 2 and 3, which is equal to 3. Since the GCD is 1, the order will be equal to 3. So the order of A is equal to the order of A squared. So the cyclic subgroup generated by A will also be generated by A squared. So D3, remember here D3 is not a cyclic group. We are just considering a cyclic subgroup of D3. So we will conclude that the order of A is the same as the order of A squared, and therefore the cyclic subgroups, the cyclic subgroup generated by A and A squared will be the same. This is the cyclic subgroup generated by A and A squared in D3. So basically this subgroup has 2 generators, for A and A squared. Are we together?
Yes.
Yeah, so a lot of this will only make sense if you have bothered to read and get all the definitions from the previous sections. So all those definitions need to be clear in your head for this to make sense. So another example, in Z10, the generators will be 1, 3, 7, and 9. So let's just illustrate this. We know that the order of 1 is equal to 10, because if you add 1 to itself 10 times, you will get 0 in Z10. 0 is the identity in Z10. So if you add 1 to itself 10 times, you will get 0. You know the order of 1 is equal to 10. Now we know that pick 3 in Z10, 3 can be written as 1 plus 1 plus 1. Now the binary operation in Z10 is additive. So we can't write them as powers, but you can think of it as 1 cubed if you are to write it multiplicatively. So if you write it like this, then you can relate it to the theorem that we proved. So we clearly know that the GCD of 3 and 10 is equal to 1. So the GCD of this means the order where 3 is this, 3 is here. The 3 we are picking is the one that is here. It just happens to be, it's just a coincidence that it's 3 here and the power here is also 3. That may not always be the case, but the 3 we are referring to is the power. So the GCD of this power 3 and the order of 1 is equal to 1. And we can therefore conclude that the order of 1 is equal to order of 3. You can use the same ideas on the other elements, 1, 3, 7, and 9, and compare. So for instance, if I want to get 7, how many times do I add 3 to itself to get 7 in Z10? Anyway, do this in your own time. Try to play around with the rest. We have just considered 1 and 3 and applied the theorem to show that the order of 1 will be equal to the order of 3. We already know the order of 1 is 10. So the order of 3 will also be equal to 10. And therefore 3 will be a generator. 7 and 9 as well will be generators. You can check those. So here is a theorem again. It says let G be a cyclic group of order n, and suppose D is a divisor of n. Again, we are very specific. This is only true for cyclic groups. So this theorem says that under these conditions, n must have exactly one subgroup of order D, a unique subgroup. As long as a cyclic group of order n and D is a divisor of n, then G must have exactly one subgroup of order D. So if G is not cyclic, this may not be true. It may not have, if G is not cyclic, then it's possible that you may not have a subgroup with D elements, even if D is a divisor of n. Have you understood?
Yes.
Good. Thank you. So now we want to prove the theorem. Let's just read it again before we prove it. We say that if D is cyclic of order n and D is a divisor of n, then G must have exactly one subgroup of order D. So that's what we want to do. So there are two things to be proved here. We need to show that there's a subgroup of order D, and it is the only one, because we are saying precisely one. We have a subgroup of order D, and there's no other subgroup. It's the only one of order D. So we say the group is cyclic, so it must have a generator. So let's call that generator A. So suppose G is generated by A, and since G has n is of order n, then the order of this L generator must also be equal to n. But we have said that D is a divisor of n, so we can write n as a multiple of D. So we choose to write n as dm, where m is some positive integer. This is because we have said D divides n, so it's possible to write n as a multiple of D. So, so we want to check. Then the order of A raised to m will be equal to n divided by the GCD of mn. This again is a formula we have proved before. I think you are familiar with this now, the one we started with. So we know n is equal to dm. We can simply replace it as dm. Oh, there's a mistake here. This should be m. So this is m and dm. The GCD of m and dm to be equal to m. I need to correct that. So this should be dm over m, so that the m cancels out and we're left with only d. Right? So using this formula, we've been able to establish that the order of A raised to m is equal to D. So we have found an element of order D, and therefore the cyclic subgroup generated by that element will have the same order. So we have shown that there exists an element, a cyclic subgroup of order D, as long as D divides n. So what's left is to show that this subgroup is unique. There can only be one such subgroup. So to prove uniqueness, let's pick any other subgroup of G, which of order D. Because G is cyclic, any of its subgroups will always be cyclic. We proved this before. We proved that any subgroup of a cyclic group must be a cyclic subgroup. So if you pick any subgroup, it turns out to be cyclic, and therefore it must be generated by some element in G. So that means since all elements in G are powers of A, the generator of H will also be some power of A. So let's call it A raised to K. So the cyclic subgroup generated by A raised to K will now be equal to H, where K is greater than or equal to 1. Now we said H is of order D and is cyclic subgroup. which means that a raised to k must also be of order d, which is the same as n over the GCD of k and n. But we know that n is the same as dm because d is a divisor of n. We are able to write n as a multiple of d. Now, because we know that this whole thing must be equal to d, it means that GCD of k and n must be equal to m, right? So GCD of k and n must be equal to m. Otherwise, this equation will not be true. And for that reason, we can conclude that k can be written as a multiple of m. In other words, m, because if m is a divisor of k, then it's always possible to write k as a multiple of m. So let's see where this leads us. So I can write a raised to k will be equal to a raised to mt, but I know that the order of a is equal to m. This is already known. And this is the same as a m raised to t. No, the order of a is equal to n. Let's not mix them up. So basically, this what we have shown here. If you pick any element in H, then it also turns out to be an element of a cyclic subgroup generated by a raised to m. So these are two groups, H, this cyclic subgroup generated by a raised to k, and the cyclic subgroup generated by a raised to m. Both of them have the same number of elements, that is d, and this cyclic subgroup is contained in this one. And they both have the same number of elements. That forces them to be equal. Right? So we have checked that the number of elements in H, which is d, should be equal to the number of elements in the cyclic subgroup generated by a raised to m. So it forces these two cyclic subgroups to be the same. So that means you can't have any other cyclic subgroup other than that one of order d. So does that make sense? Are there any questions? Are there any questions? Hey, can you hear me?
Yes.
Oh, okay. So have you understood what is on the... Although, like I said, some of these things you really need to take time and read, maybe watch the video again, read the notes again until you understand it. And the best way to learn this is to write these things down. Don't just stare at the screen. You need to find a place where you are able to do some writing. If you don't write them down, they will not make sense. Okay, so now we move to a new topic. We call these, we are going to define cosets and do some work on cosets. So the first definition we have is we define a left coset. So we have, let H be a subgroup of G and let A be an element of G. So we define this set AH, which is equal to A small h, where H is an element in the subgroup. So this set is simply called the left coset of H in G determined by A. So it means for different elements of from G, we'll be able to construct possibly different left cosets. So you can keep changing the elements A from G and you keep getting a new set. So how you construct this set is simply pick every element in H multiply it on the left by A. So the new set that you obtain is what we will call the left coset of H in G determined by A. So I think there are some people trying to join. Let's see if we can let them in. Okay, so let's continue. So you can see that's the left coset of H in G determined by A. We shall see some examples shortly. We will mostly work with the left coset, but it's also necessary to define the right coset because there are a few situations where we shall need to talk about the right coset as well. Now, let H be a subgroup of G and A be an element of G. Then this set here, this is wrongly written. This should be HA. A should be on the right. The same on this side. So for right cosets, we need this. The order here should be changed. H should be on this end so that you have HA, and also here you have HA. So that's a mistake. I think I've repeated the same left coset here. This should be the right coset, and right simply means you multiply by A on the right. So note that down, but I will also correct it on the slides. I'll just note it down so that I remember. Now next, we look at construct some of these left cosets. So we can pick this, the group of integers modulo 10. Remember, if we just say Z10 without specifying the binary operation, what do we mean? What would the binary operation be?
Addition.
Yes, addition. Modulo 10. So it's addition modulo 10. So here we pick a subgroup of Z10. So this is a cyclic subgroup generated by 2. So if you get all the multiples of 2, this is what you end up with as a cyclic subgroup of Z10. We have constructed cyclic subgroups before. So I think you can construct this on your own. Now I can just claim it is a cyclic subgroup generated by 2. So we compute the left coset of H determined by 9. So how we do that is we add 9 to every element in H. And the new set of numbers that we obtain will be our left coset of H in Z10 determined by 9. So remember, the binary operation is addition. So that's why instead of 9H, you have 9 plus H. So because our binary operation is additive, the left coset will be written like this, 9 plus H. If you check the definition, we just wrote this as AH. So here the assumption was the binary operation is written multiplicatively. So that's why there's no operation between A and H. But if it's written additively, you put the operation plus here. So 9 plus H is the left coset of H in Z10 determined by 9. So we do this, we add 9 to every element in here. And 9 plus 0 will give us 9. 9 plus 2 is 11, which gives us 1 modulo 10. Okay, this should be 9 plus 3. No, 9 plus 4. 9 plus 2 is done twice. It should be only once. I think it's repeated here. We need to delete one of them. So 9 plus 4 is 13, which gives you 3. 9 plus 6 is 15, which gives you 5 modulo 10. And 9 plus 8 is 17, which gives you 7 modulo 10. So I've just chosen to arrange the numbers in the set in ascending order. So here they are all there's no order here. So just to make it look neat, I've rearranged the same numbers to get the same set, but now in some kind of order. It doesn't matter. Even if you left it like this is still correct, but this just looks neater. So this is the left coset. This set with the numbers 1, 3, 5, 7, and 9 is the left coset of H determined by 9 in Z10. So I can give you a few minutes. Can you determine the left coset determined by 3? Just work this one out alone. The left coset of H determined by 3. So the first person to get this one gets 100 MB.
Getting 1, 3, 5, 7, and 9.
Exactly. It's the same as the left coset determined by 9. You can see. So you will have to remind me to send the reward. Who was
Yes.
it?
Isaac.
Wakanene? Or which
Yes,
Isaac?
yes.
Oh,
Yes,
okay.
Isaac.
Okay, good. So you can try with all the other numbers. What you will notice is if you pick any number that is already in here, it will generate exactly the same left coset. So 7, 5, 3, 1, and 9 will all generate this same coset. So what about, let's do another example. We have T3, the dihedral group. Remember we chose to write the elements of a dihedral group in this form. You just need to recall the defining relations. Then you write it, all the elements in this form. Then we have the subgroups. We pick 2 subgroups.
Teacher, you have a lot of background noise.
I know there's someone who has put on their microphone. I think now it's off. Sounds clear on my end now. So we will be looking at that example in a minute. So the dihedral group of degree 3 has these 6 elements, and the subgroups, we select these 2 subgroups. This is a cyclic subgroup generated by A, and this is a cyclic subgroup generated by B. So those 2 are subgroups. So these are the defining relations. Remember that A cubed and B squared will give you the identity, and B inverse AB is just the same as A inverse. And we know that A inverse is the same as A inverse is the same as A squared. The inverse of A is just A squared. If you multiply A and A squared, you get the identity. So the inverse of A is just A squared. So these are just useful for computations. So let's compute the left coset of H. H is this group, subgroup. And we want to compute the left coset of this subgroup H determined by B. So BH will simply mean you multiply every element in H on the left by B. So we multiply this, and when it says left coset, you must multiply on the left. So that would be BE, BA, and BA squared. We have all of them here. So using these defining relations, it's possible to simplify this or to rewrite these so that they look like what the elements in this set. So BE is the same as B. BA, I think, should be the same as A squared B. Is that correct?
Yes.
And BA squared should be the same as AB.
Yes.
Or is it in that order? I can't remember. Just check that. But eventually you will get these three elements. So let's try to, if you pick an element A in H, then AH will simply be AE A squared A cubed, which gives you A squared E. Again, so here it means you still get H again. So if you pick any element already in the subgroup, for instance, this A and A squared, they're already in the subgroup, they generate, the left coset will just be the subgroup itself. You can see that. So let's just go back. Remember, now we get the left coset of this subgroup. K is equal to EB, the cyclic subgroup generated by B. So if you get the left coset of K determined by A, then you need to multiply everything in K on the left by A, so that you have AE, AB. AE is just A and AB is just AB. So that's the left coset. A squared K will be equal to A squared B, and last but not least, ABK. If you pick AB, and ABK will simply be ABE, and then AB multiplied by B, which will simplify to AB and A. B squared is just the identity, right? So AB squared should be equal to A. So that gives you all the. Now, if you try to pick to get the left coset determined by A squared B, which is already in this left coset, you still end up with the same left coset. This left coset and that left coset are the same. So any elements that are in the same left coset will generate the same left coset. We shall make this formula in a while. But for now, we are just setting them as facts. But there's a theorem that will show us how to confirm all that. Okay. So now you have an exercise here. You compute the remaining left cosets of H. I think the ones we didn't compute in the first example. You can now compute them. You'll do this in your own time. But you can note it down. There's someone who has put on the microphone again. So are there any questions on this part? Should I double the speed?
No.
You are happy? Okay, you are. I don't know whether the silence means you're happy or not. So there's some more work here for you. It says let H be a subgroup of G, and let A be an element of G. So you need to prove that the left coset determined by A will be equal to H if and only if A is already an element in H. So this is useful when determining left cosets. If you want to find left cosets, you should simply stick to elements that are already outside the group so that you can find a new left coset. And also this tells you that one of the left cosets will be the subgroup itself. So the subgroup itself is always one of the left cosets. Then you can find other left cosets by trying to obtain the left cosets determined by elements that are already outside the subgroup. If you pick elements that are already in the subgroup, they won't give you anything different from the subgroup itself. So this is some work for you to do. Prove this one. And then the second one is to determine all the left cosets of 2z in Z. Now 2z here simply means all multiples of 2, or if you like, the even numbers. We know that this set is a subgroup of Z under the usual addition of integers. So your work is to find the left cosets of this subgroup 2z in Z. So what is interesting about this, you'll actually find exactly 2 left cosets. The interesting thing about this example is that you have two infinite. It's an infinite group. The subgroup is also infinite, but the number of left cosets is finite. You have 2 left cosets, exactly 2 left cosets. Now you can in your own time try to find them. If you have any questions, we can address them next time. Any clarifications you need for this? Hakuna? Good. Anyway, I hope you have noted them down. Then in your own time, you prove this first one and also construct the left cosets in the second exercise. So we make the following observations when we are computing the left cosets of K in the dihedral group. Now, the subgroup itself was K, and the left coset determined by B will also be equal to K. So then we also found this left coset, which is the left coset determined by A squared. And then there is also this other left coset, which is a left coset determined by A, the left coset of K determined by A. It will also be the same left coset determined by AB. Right? AB and A will determine the same left coset. So you could say the same up here. A squared and A squared B will also determine the same left coset. And E and B here will also determine the same left coset, which is just the subgroup K itself. So what we're trying to say here is the following, that these are the only distinct left cosets. Any left coset you try to compute will coincide with one of these. You can't get any other left coset. These are the only 3 left cosets of K in B3. Are we together?
Yes.
In addition, you'll observe that these left cosets don't have anything in common. None of the elements here will be found in any of the other left cosets. So the left cosets here, the distinct left cosets are disjoint. So later on, we shall figure out how we can tell that 2 elements determine the same left coset. So like in this case, you have A and AB, they determine the same left coset. You have A squared and A squared B will determine the same left coset and so on. So later on, we shall see how do we tell if 2 elements will determine the same left coset, 2 different elements. But here we since there are finite number of elements to check, you can check that these are the only left cosets you can of K in the dihedral group that you can obtain. So now we move on to something more formal now, away from the examples. So let H be a subgroup of G. We're going to define a relation on G as follows. We say A will be related to B if A inverse B belongs to H. So we have defined a relation on G. And that means if you pick any two elements in G, we shall say that A is related to B if A inverse B is in H. So the two being related is determined by this condition that A inverse B must be in H. So we claim that this is an equivalence relation and proceed to show. Now this is a mistake again. This should be A inverse A. A inverse A, not A raised to 1. So we can check that A inverse A is the identity, but the identity must be in H. H is a subgroup, so it must contain it. Someone needs to switch off the microphone, please. Can someone check and tell them, whoever that is?
No more.
There's more.
Yeah, try to keep the microphones off, but when you have questions, you can switch it on and ask the question. So A inverse A is equal to the identity element in H. And that means under this relation, A is related to itself. So this relation is reflexive because every element in G will be related to itself. So we have two more properties to check. The second property is a symmetric property. So here, if A is related to B, by definition here, it means that A inverse B will be in H. But now H is a subgroup. So the inverse of any element in H will also be in H. So if you get the inverse of A inverse B, we end up with B inverse A. But since H is a subgroup, B inverse A will also be in H. And that means if we use this relation, it means B is also related to A. Because if you switch these two, what you will have here is B inverse and A to show that B is related to A. So this relation is symmetric. We've established that. Now the last thing is the transitive property. So here, if A is related to B and B is related to C, then by definition A inverse B, by definition of the relation, A inverse B and B inverse C will both be in H. So what we need to check is if A will be related to C. If you can prove that, then we'll have shown that the relation is transitive. So A inverse C, we need to show that A inverse C is in H. If we can show that, we are done. So we can rewrite A inverse C as the product of these two. This is because B and B inverse will go if you expand this. So, but we know that A inverse B is an element of H because A is related to B, and B inverse C is an element of H because B is related to C. And therefore, since H is a subgroup, the product of any two elements of H must be in H. And therefore, we can conclude that A inverse C must be in H. And this, according to our definition of a relation, it means that therefore A must be related to C. And this leads us to the conclusion that the relation defined here is transitive. And since all these three properties are satisfied, we now say that the relation is an equivalence relation, which is a claim we made at the beginning. So are there any questions on this? So remember the correction up here. This should be A inverse, not A raised to 1. It should be A inverse.
Hello, sir.
Yes.
Yes. I beg your pardon. I'm not understanding how you are defining this relation.
It's quite clear up here.
It's quite clear.
Read it twice first before I talk. Read it not loudly. Just read it out to yourself silently. So we want to define a relation on the set G. So we want to check how are two elements in G related. So we fix H is fixed as a subgroup. To pick any subgroup, and fix it. Then define the relation on G. That means pick any two elements in G. Those two elements will be related if the inverse of A multiplied by the inverse of B will be in H. That is all. What is not clear there?
It's not clear.
Okay. So we now compute since anytime you have an equivalence relation, as a mathematician, you get excited and you want to find the equivalence classes. So that's what we are going to compute now. So we shall denote the equivalence class of an element A by C of A. So this notation here will mean the equivalence class of A. So this is not standard notation, but it's convenient for us now to use it. Some books may use a different notation for the equivalence class. So, but what is the equivalence class of A? The equivalence class of A is simply all the elements related to A. All the elements in G that are related to A. So we start by that definition. But we know that any element A will be related to X. For any element X, A is related to X if A inverse X is in H. That's how the relation is defined. So how do we figure out which elements are in here? We make some substitutions. If we fix Y to be A inverse X, then we can rewrite X as A multiplied by Y. How do you get that? We simply pre-multiply both sides of this equation by A. So you get, here you're left with X and you're left with AY on the right. So that X now, if we set Y to be equal to A inverse X, then X will be equal to AY. So then we can write this equivalence class as follows. We can write it as, replace now X with AY in G such that Y is in H, right? Y is just this element, an element in H. But now this is precisely the definition of a left coset of H determined by A. So basically what we are claiming here is that the equivalence class of A is just the left coset of H determined by A. So that's how you obtain the equivalence classes. So one of the properties of an equivalence class, one thing that equivalence relation does to a set is it partitions it into disjoint subsets whose union is a whole set again. So this one you must have done in basic mathematics. So the equivalence relation will induce a partition on G, and the equivalence classes will simply be the distinct left cosets of H in G. So what this says is that you can split the group into the distinct left cosets, and the union of those left cosets will give you the whole group. That's what it means, what partition means. Let's just go back to, from this example, you can see these distinct left cosets actually partition D3. If you put D3, these three distinct left cosets, if you get the union, you will get the whole of D3 again. So these left cosets have actually partitioned D3 into three disjoint subsets. The other thing you need to take note of is that each left coset has exactly the same number of elements as the subgroup. K had 2 elements, and every left coset of K has exactly 2 subgroups. So we shall also see that in a formal way. So this is what we have just looked at. We have seen that the equivalence relation will induce a partition on G. And the equivalence classes are simply the distinct left cosets of H in G. There's a spelling mistake here. They should be distinct. So now let's put that in a more formal way. So what we have said there basically is the following, that if H is a subgroup of G, then G
Excuse.
can be written as a union of, yes?
Could you go back to the other slide? No, the slide after this one.
After or before?
After this one now.
This one.
No, not before the theorem. Before the theorem. No, not here. You're very behind. Go ahead. Yeah. Thank you. Just a second. Okay, thanks.
Okay, so we can proceed now. So remember, if you have an equivalence relation on a set, then it's always possible to write that set as a union of all the equivalence classes. So this is what this first statement says. It's basically a consequence of having an equivalence relation. We already established that the equivalence classes are these distinct left cosets, or rather the left cosets, if you just want to call them that. The union of all the left cosets will give you back the whole of G. That is directly from the properties of equivalence relations. Then the other thing about the equivalence relation is that it induces a partition on the set. So here can someone, you need to keep your microphones off, please. If someone was switched on.
Johnny.
So another thing you should learn to do, please try to do this in an environment where you'll have very few distractions. Unless it's completely impossible for you to be in such an environment, then that will be understandable. But if you can, try to, it's only 2 hours, and after that, you'll be able to go and do everything else you wanted to do. If you wanted to listen to the music, you'll have plenty of time to listen to. The music will not go anywhere. Am I right or am I right?
You are right and right.
You're right.
You're right.
Sorry
Sorry for that.
Huh?
Sorry for that.
No, I don't be sorry. It's for your own good that you switch off that music, not for us. For us, we were enjoying the music.
It wasn't mine.
Oh, it wasn't yours. No, music is good, but it's we for your own purpose. Whoever had them on, it is important that you are in an environment where you can pay full attention to this. So anyway, any two equivalence classes will either be disjoint. If they are not disjoint, they will be equal. But we already established the equivalence classes to be the distinct left cosets. So here we are claiming that any two left cosets of a subgroup will either be disjoint. In other words, the intersection will be empty. If that is not true, then they will be equal. And when they will only be equal if A is related to B, and A is related to B if A inverse B is an element of H. So again, these are very useful statements. That you can apply. So make sure you spend time on this and try to clearly connect them to the ideas in this section where we're talking about the equivalence classes. So basically, we have what I've stated here is what we have proved earlier using the equivalence relations. But now here it is stated a little more formally. So I will not go into the proof of this because we have actually done it.
Okay, excuse.
Yes.
Okay, I have a question. Okay, just pardon me because I will take you back. For the coset, the left and the right.
How many slides back?
Okay, just go. I think 4.
I think I should put page numbers on the slide so that you can.
Yeah, yeah, there now. Okay, go one step ahead. Yeah, okay, fine. For example, another step, and okay, fine. You can just stop there. Go back. Sorry. Yeah, for this one, for
Yes.
the one which is saying the left coset of H determined by 9 is whatever is given there. Now I was inquiring like, yeah, for H, like you've been given is 0, 2, 4, 6, 8, right? And then
Yes.
for 9 plus 8, you're supposed to compute something. Now I was inquiring
Yes.
if are we supposed to take just any number from whatever is contained in H, or what?
Can you ask your question again? You are supposed to take what?
Like, okay, fine. Okay, the question is saying, the example is saying consider Z, okay, and then you've been given some values, and the subgroup of H have also been given some values.
This is not Z, it's Z10. Z10 is a integers modulo 10.
Okay, fine. The left coset now of H is determined by 9, which is you've already been given 9 plus H, okay, and then conditional of brackets. Okay, now my question is, like, for us to compute whatever the 9 plus H, we understand that you're supposed to take something. Okay, now the question is, this is the question, like, are we supposed to take any number which is in the,
yes, if you want to determine the left coset of H determined by 9, you take 9. If you want to get the left coset of H determined by 8, you take 8. Okay?
Yeah. Okay,
so
fine.
here we
And
only
then,
computed one example. Huh?
Yeah. Okay, and for this one, and for for the quiz you gave, it was 3 plus H, 1 plus H, right? And then you say that the values you can kind of will be the same with 1 plus 3, 5, 7, 8.
Yes.
Right?
Now simply compute them. Have you computed them?
So,
simply add 3 to all these.
What? Pardon?
So if you add 3 to all of these, let's compute them. Let's have more action and less talk. If you have 3 plus H, add 3 to every element in H. So let's start. Do you have a paper to write down?
Yeah.
Yeah, get out your paper and pen. That's why I insist that you must pull out your pen and paper. Otherwise, yes. So the first thing is to add 3 plus 0 will give you what?
3.
3 plus 2 will give you what?
5.
3 plus 4?
7.
3 plus 6?
9. 11.
11 does not exist.
It is 1.
11 will give you 1. So you end up with the same numbers. 1, 3, 5, 7, and 9, right?
Yeah.
So 3 and 9 will give you the same left coset, right?
Yeah.
What about 1 plus H will give you what? So any element you pick in here that is already in this left coset will give you the same left coset.
Okay.
So for instance, if you compute a left coset determined by 9, if you want to get a new coset, don't use any element that is already in the left coset. You have to pick something outside here for you to get a new left coset.
Okay.
So for instance, if I want a new left coset,
for example, I'm not supposed to take like 1, 3, 5, 7, but to take something to do with 9, 1, 3.
If you want a new one, you have to take something outside here. I think that is very clear. You are taking us back and forth on very clear.
Outside.
If you want a new left coset, pick an element that is not in this
Okay,
set.
you may get. Now.
So, but and then this one requires you to do a lot of practice. So don't sit back and relax.
A question on the same, Mwalimu.
Yes.
Unasema the left coset we pick numbers outside the given elements.
You can pick any number. Listen. Pay attention.
Yeah. Yes.
Give this your full attention. You can pick any number in here, compute a left coset. Right?
Yes.
So we gave an example where we got the left coset of H determined by 9. And we found that 9 plus 8 will be the set that contains this. Maybe you should put on your earphones so that you don't have echo. So we found that the left coset determined by 9 is this left coset. So if you want, you can, in your own time, try to compute the left coset determined by the other elements that are already here. So if you want the left coset determined by 3, we have seen the left coset determined by 3 also gives you exactly the same elements here. You don't get a new set, right? The same will happen with 1, the same will happen with 5, the same will happen with 7. This is something you must do in your own time. I can't compute everything on this in class.
Yes.
Yeah. So now what I'm saying is, and we have seen this already in the theorems that we looked at later, that if two elements under the relation, the equivalence relation that we defined on the group G, two elements will give you the same left cosets if they are related under that relation. So any elements in the same left coset will be related and therefore must give you the same left coset if you use them to determine a left coset. So what I'm giving you is a shortcut. If you have already found a left coset determined by 9 and it contains all these other elements, for you to find a new left coset, you will have to pick an element outside here. Otherwise, you will be repeating yourself. You will end up getting this same left coset how many times? 5 times. And so it won't give you anything new. So if you want a new left coset, different from the one that you already have, compute the left coset determined by an element outside this left coset. So that will give you a new left coset. So if you pick, for instance, if you pick 2, 2 is already, all the elements outside here are just the elements in H. So if you want, the other left coset will be H itself. So if you pick any element in H, 2 plus H will give you H. 4 plus H will still give you H, and so on. So the two left cosets are just H and this other left coset, the left coset determined by 9. So there are two distinct left cosets. Their union will be the whole of Z10. So once you find the left cosets and you realize that their union is the whole group, then you don't need to look for any more cosets. You found all the distinct left cosets. Is that clear now?
Yes, very clear.
So the important thing is you need to pay attention. Pay very keen attention to everything. It will make things a bit easier for you. So where were we? We had were somewhere here, I think. So the same ideas that you see here are what I've been talking about in that example. If H is a subgroup of G, then you can always write G as a union of its left cosets. And any two left cosets are either disjoint, in other words, the intersection is empty. But if they are not empty, they will be equal. And when will they be equal? They will be equal if, so AH will be equal to BH if A inverse B is an element in H. Are we together?
Yes.
So the target usually will be to find all the distinct left cosets. So once you find one left coset, you can try to find a new one. And I've shown you how to find a new one. So let H be a finite subgroup of a group G. Then any left coset of H has the same number of elements as H. So if H has 10 elements, any left coset of H will have exactly the same 10 elements, the same number of elements. Not the same elements, but the same number of elements. The left coset will also have 10 elements. Now, the proof for this is as follows. If you have any two finite sets, if you want to prove that they're equal, one way of doing it is to find a bijection between the two, to find a map that is one-to-one and onto between the two sets. So that's what we shall do. We will construct a bijection from H to any left coset of H. So we construct this map from the subgroup H to any of its left cosets. A is some element from G. So we define it as H is mapped onto AH. So this map is bijective, as we shall see. So if the image of H1 under the map is equal to the image of H2, so what this means is that AH1 is equal to AH2, but then this again means that H1 must be equal to H2. If you apply the cancellation laws, you can get rid of the A on the left, and this means H1 must be equal to H2. But then this implies the map is injective. The surjective bit is a little obvious because any element you pick in here will be of this form, A multiplied by H, where H is some element of a subgroup H. And such an element will clearly have a preimage of H. H will simply be mapped onto AH. So there's none of the elements here will be left out. It will be a surjective map. Every element here will have a preimage. So that means this map from H to AH is bijective. And since H and AH are both finite sets, they must have the same number of elements. So if a subgroup has two elements, any of its left cosets will always have exactly two elements. And we have seen that in the examples. We already illustrated this theorem. Any questions on this? No questions?
Yes.
The correct answer should be no if you have no questions. So based on what we have discussed, we can set up some definitions. So let G be a group and H be a subgroup of G. Then the set of all left cosets of H in G will be denoted by this G, and then we have this / H. So this is a forward slash, not a vertical slash. You must get that very clearly. So when you're writing this down, don't write it as a vertical line. It's a forward slash. It's slanting. So the set of all left cosets of H in G will be denoted by this. We shall look at some examples shortly of how to use this. So then the next thing we need to define is the index of a subgroup. So if H is a subgroup of G, the number of distinct left cosets of H in G will be called the index of H in G. Now the index of H in G will be denoted by, you have G, then there's a full colon between G and H, and these two vertical lines on the end. So when you see this, what this simply means is the number of distinct left cosets of H in G. Any questions? Okay, so let's look at some examples. So we had looked at this earlier, the dihedral group of degree 3, and this subgroup H, which consisted of these three elements, E, A, and A squared, and we already established that this is a cyclic subgroup of D3 generated by A. That's why we have this. This notation means a cyclic subgroup generated by A. So we try to get the left cosets of H. One of them is H itself. We can get it by getting any left coset determined by one of the elements already in H. So we pick AH, give us this as one of the left cosets, and BH to give us this as our second left coset. So the set of all distinct left cosets of H in G is therefore, it simply consists of these two, AH, which is equal to H, and BH, which is the second. You can try to generate these left cosets using other elements in D3, but you won't get any new left cosets. You'll either get this one or this one. You won't get any new ones. So the only two distinct left cosets are these ones, H and BH. Is that making sense? So
Yes.
now that the distinct left cosets of H in D3 are exactly 2, we can now say that the index of H in D3 is 2. Or if you want to use our notation, you use this notation. This simply means the index of H in D3 is equal to 2. And that means the number of distinct left cosets of H is exactly 2. The 2 comes from here, the 2 distinct left cosets. Any questions? Let's look at another example. This time we consider a group of integers modulo 6. So we pick a subgroup of Z6. So we pick the cyclic subgroup generated by 3, which will have 0 and 3 as its elements. I believe this should make sense because we already learned about the cyclic subgroups. If you have any problems, you can always go back to the video and watch. So we now compute all the left cosets of H in Z6. Again, remember in Z6, the binary operation is written additively. That's why we write the left cosets like this, with plus. So 0 plus H will give us H itself. And it's the same as what you get if you try to get 3 plus H. So 0 and 3 will give you H as one of your left cosets. 1 and 4 will give you this left coset, 1, 4. They both, 1 and 4 both give you the same left cosets, 1, 4. You can check that because 4 plus 0 is 4 and 4 plus 7 is 1 modulo 6, right? 2 and 5 will also give you the same left coset. So the distinct left cosets will be, this will be the 3, because if you put them all together, you end up with the whole of Z6. So the union of all this gives us Z6. So it means we have found all the distinct left cosets. There are no more to look for. So therefore, the set of all left cosets of H in Z6 will simply be consisting of these three left cosets, we can pick H, 1 plus H, or 2 and 2 plus H. You could replace 1 plus H with 4 plus H, or 2 plus H with 5 plus H. But I think this works better for me. I'm happier working with the smaller numbers, 1 and 2. So now that we have found three distinct left cosets of H in Z6, that means that the index of H in Z6 is 3. And here observe that Z6 is a union of these three left cosets, H, 1 plus H, and 2 plus H. And also what we mentioned earlier, I am repeating here, also observe again that the left cosets will never have any elements in common. The other thing to observe is that the subgroup H has 2 elements, and each left coset has exactly 2 elements. Any questions? Nani ana swali? So let's see if we can put all this together. We have said a lot. Now we want to make it concrete. So we'll summarize again what we have just done. We have said that let H be a finite group, and let H be a subgroup of G. So let G be a finite group and H a subgroup of G. So we pick no, this is wrong. V should be a subset of G, not a subset of H. So I need to pick a subset of G. V is a subset of G such that for any other X in G that I pick, there is exactly one element A in V such that XH is equal to AH. So I pick a representative which gives me exactly one of the distinct left cosets. So for each of the left coset, I just pick one representative, and I set up my new set V, which should be a subset of G, not a subset of H. So this should be G. Please note that correction. We call V the representative set. So we have determined the following. We know that the number of elements in every subset here, subgroup, will be equal to the number of elements in any of its left cosets. This is established. We have seen that. Similarly, we know that the G will be the union of all the distinct left cosets. Now, the union of all these distinct left cosets is a better union than the one we had before, because now we are using representative sets. The previous representation was a bit wasteful because we were using all the elements from G, but now we are picking only elements from the representative set so that we have only the distinct left cosets in this union. Is that making sense? So now, under these circumstances, if the number of elements, if the order of G is n, so the number of elements in G is equal to n, and since G is a finite group, H will also be a finite group, and therefore it will have a finite number of elements. Let's call them M. And using these ideas here, we will see that G consists of these subsets, each of which have the same number of elements, and therefore there must be M must be a factor of n, right? The number of elements in H must definitely divide n, because you have split G into a number of subsets each of which have the same number of elements. So that means M must divide N, and therefore we can write N as a multiple of M, where K is just the number of distinct left cosets. We shall go back to look at the details of this in more shortly. So what we have just put there is the following theorem. It says that let G be a finite group and let H be a subgroup of G. Then the order of H divides the order of G. So the number of elements in H will always be a factor of the number of elements in G. So for instance, if G has 10 elements, its subgroup, the only possible orders of a subgroup will be either 2, which is a factor of 10, 5, which is also a factor of 10, and 10 itself. That is the whole group. So if the group is of order 10, you can't have a subgroup with 3 elements, because 3 does not divide 10. You can't have a subgroup with 7 elements, because 7 does not divide 10. So that's what this says. So look at these two statements carefully. And then we can go back to an example here. So here's an example. Z6 has exactly 6 elements. So the order of Z6 is 6. We picked a subgroup which has exactly 2 elements. So if you were to use the theorem, N here will be 6 and M will be 2. Okay. So our claim is that M must divide 2, and that is true because we have 3 distinct left cosets. Each of them has exactly the same number of elements. So here, if you multiply 2 by 3, you will get 6, right? The number of elements in Z6. So in our case here, K will be 3. So 6 will be equal to 3 times 2. And now you can set up a representative set as follows. So your representative set can be 0, 1, and 2. Because if I pick 0, 1, and 2, any other element I pick from Z6 will simply give me the same left coset. So I don't need the others anymore. I just pick my representative set to be 0, 1, and 2. And I get the union using that representative set. Then I get just the union of these 3 distinct left cosets. So you could also choose your representative set to be 3, 4, and 5. That would still work. Or 0, 4, and 2. That will still work. But I find it neater to pick 0, 1, and 2. And maybe that is easier to keep track of. Any questions? So this Lagrange's theorem is very important. I think it's the most important theorem in the world. You agree? You can hear me?
Yes.
Yes, sir.
So basically it says if you have a subgroup of a finite group, then the number of elements in the subgroup must be a factor of G. Okay. So the converse of this theorem may not be true, and that means if you have a factor of G, then it's not a must that it must have a subgroup of that order. So if D divides G, it's not a must that the G must have a subgroup of that order. But earlier on we saw if G is a cyclic group, then this will always be possible. So for cyclic groups, the converse is true. For cyclic groups, if D divides the order of G, then there must be a subgroup with exactly D elements. When we are working with a symmetric group, we'll get an example to show that it's not always true that if D divides the order of G, then G must have a subgroup of order D. So when working with the symmetric group, we shall give an example of this. There's a group, the alternating group, A4. We shall look at that. It's a good example of this. A4, I think, does not have a subgroup of order 6. It has 12 elements, but does not have a subgroup of order 6. But since we don't know what A4 is now, we shall deal with that when we are dealing with the symmetric group. So I think that's a good place to stop. We'll start from there next time.
Thank you, sir.
Is there any questions? Any questions from the class?